Hey everyone, we are starting our intro to the washer method. This is following off of our disk method video, finding volumes of solids of revolution using the disk method before. We're going to do something very similar called the washer method. At the end of the last video, we hinted that if your region, so here's my region that I'm going to revolve, and I'll revolve this about the x-axis. If it's not in contact with the axis of revolution on the interval, so in other words, here from A to B is sort of the shadow it casts on the x-axis. It's not in contact with the axis, so when we revolve this and generate a solid, we will get some hollow space in the middle. I'll go ahead and show you that now. So if I take this region and I revolve it about the axis there, then we get sort of a bowl-like shape. And before, when we cut through, we got solid disks, and here if we cut through, you'll notice we get some hollow space, so we actually get washer shapes where it is a disk, but there's also a smaller disk cut out inside of each slice that we would make. So if we're revolving this, we're going to get some missing space in the middle. So what we'll need to do is figure out how to use disk method, but instead of using each slice being a circle or a disk, what we'll want to do is then change our method to sum up an infinite number of washers. And so we will need to first figure out how are we going to get the area of a washer. So you may already know that, but if you don't, we'll go ahead and figure this out. So again, this is my region R. We're going to revolve about the x-axis. And I'm going to go ahead and line this washer up with the region as well. So if I were to find the area of this washer, then what we would really do is we would take the area of the entire big circle. So we'll say the area of a washer. And that would be the area of the big circle minus the cutout section, the area of the little circle. So if you imagine the area of the big circle, formula for the area of a circle would be pi r squared, right? So I'm going to go ahead and say the area of the big circle is pi r squared. And I'm going to use a capital R so that you know that this is the bigger circle. And then we go ahead and look at subtracting out the area of the smaller circle. And so this area here would be pi times a smaller radius squared, right? So this distance here is going to be little r. So to do that, we'll have pi times capital R squared minus pi times little r squared, and that will give us the area of a washer. Now, the size of each washer is changing. As we move from A to B, we're going to get sometimes not very much space in the middle. The outside size is also changing, so a lot of these are changing. If you think about revolving this, our boundary curve that is farthest away from the axis of revolution, that's going to be our larger radius. So this is going to be our larger radius, and it's not always the same. We're going to call it capital R of x, right? This is changing depending on which x value we choose between A and B. So this one here is our inner radius, the one closer to the axis of revolution. So this is going to be our little r of x. So each washer created is going to be capital R minus little r squared multiplied by pi. The way we will figure this out as an integral is we need to look at our rectangle the same way that we did with disk method, in that our rectangle that generates each washer as we revolve it around will be perpendicular to the axis of revolution. So if I'm running my rectangle this way, then that tells me in this example that I will be integrating dx. Okay, so what we need to then do is change these from just a capital R squared and a little r squared to actually functions of x. So we're going to get that volume equals, now if you'll notice we have a pi in both of these terms, so I could factor out the pi. I'm going to do that for our formula, so we'll get pi times the integral from A to B, and we will have the big R squared, except it will be a function of x. So we'll have capital R of x squared minus little r of x, that function squared as well, dx. And again, remember this one is the farther curve from the axis of revolution, and this one here is the closer curve to the axis of revolution. Be sure also to notice that you are squaring each of these separately, not doing capital R minus little r and then squaring. That would be different in most cases and not something that we're going to want to do. It's a very common mistake. Okay, so just the formula for washer method here in our intro video. You can see we have it again written here. Important things you need to remember. This is very similar to disk method. We're just subtracting out this inner space that is missing there. So the rectangle for deciding integral dx or dy, make sure it's perpendicular to your axis of revolution, just like in disk method. Again, keep your capital R and your lowercase r straight, capital R farther, lowercase r is closer. A lot of times when we're doing f minus g with integrals, we think higher function versus lower function, or right function versus left function. Those don't really apply here. It needs to be the one that is farther and the one that is closer to determine capital R, lowercase r. And again, you know, don't fall for the mistake that happens occasionally where people will do capital R minus little r and then they'll square everything once they've put it together. Use the order of operations here correctly. Square each piece separately, then do the subtract, and then do your integral from a to b. Okay, so I'm going to go ahead and do an example video after this that actually works out the volume of the solid that we showed here in this video. So check that out. We'll work all the way through that one for you, and we'll see you in the next video.